In this lesson, we'll discuss the relationship between power and energy. By the end of the lesson, you'll be able to define power and energy as units of measure, calculate power and energy using voltage, current, and time, and interpret the instantaneous electrical measurements and time of use electrical measurements. So why is this important? Let's look at a real-life scenario. Look at an electrical input of any appliance. It either has a power rating listed as some number with a W next to it, or a current and voltage rating. Well, what do those mean? And how do we assess what they mean for electrical needs? And how do we determine the appropriate solar panel system that would fit the needs of a specific device or maybe a whole building? Let's start by looking at the unit of power. Power is typically defined in watts or kilowatts. Kilo is the SI notation meaning 1,000. Power is the rate of doing work or rate at which energy is used, produced, or transferred. More simply, power is just energy divided by time, and a common unit is W, or watts. What can we do with this unit? In a previous lesson on efficiency, we looked at power calculations. Again, watts can be calculated as voltage multiplied by current flow, or amps. The watt is also the primary unit of power measurement used in all electrical systems, including photovoltaics. As an example, you might look at a clothes dryer which operates at 220 volts and 8 amps. So we can calculate the power by multiplying 220 volts by 8 amps, which equals 1,760 watts when in use. Another example would be a photovoltaic panel which operates or outputs 40 volts at 5 amps. Multiplying those together, we would get 200 watts when operating. A third example, which just moves around the variables, would be to say look at a whole photovoltaic string, which would be just several photovoltaic modules wired in series. If that system produces 1,300 watts and outputs 224 volts, divide those by each other, we can then figure out that the current flowing through the system is 8.03 amps. So there are 3 different ways that we can calculate power. Now let's look at what power has to do with energy. Well, as we just saw, power is defined as energy divided by time. So energy is power multiplied by time. Energy includes how long a device is being used or how long it's producing power. There are many units for energy, such as watt hours, kilowatt hours, BTUs, which stand for British Thermal Units, joules, and calories. Calories also happen to be the same energy unit that we use to describe foods and burning of calories. Energy for electricity is typically measured in kilowatt hours or watt hours when being consumed or produced. Coincidentally, sunlight energy is also measured in kilowatt hours or watt hours. Knowing this, we can compare the sun's energy output to photovoltaic energy and electrical load, or the demand, using this common unit of kilowatt hours or watt hours. It's a direct comparison. So how do we use that energy value? Well, again, since energy is just power multiplied by time, we can look at everyday appliances like, say, a hairdryer or a light bulb. In the case of a hairdryer, it might use 1,100 watts when it's on. Well, let's assume it's on for 15 minutes per day or 1/4 of an hour, and using that 1,100 watts. One might use that same hairdryer for about 180 days per year. So we can then multiply the 1,100 watts by the 1/4 of an hour, or 0.25 hours, by the 180 days that it's in use per year. That means that the hairdryer consumes 49,500 watt hours, or 49.5 kilowatt hours per year. That power value might seem high, 1,100 watts. So let's compare it to something which consumes a little bit less power, like a light bulb. If we take a 60-watt light bulb and use it for 4 hours a day, and just about every day of the year, say 345 days, we would multiply the 60 watts of the light bulb by the 4 hours of use per day, multiplied by the 345 days per year. That equals 82,800 watt hours, or 82.8 kilowatt hours. So even though the light bulb has a lower power rating of only 60 watts, it consumes much more energy over the course of the entire year. So that's why power and energy are both very important units. The power tells us about the instantaneous consumption, and the energy tells us how long that electricity is being used or produced. So the important value that's needed for energy is always going to be time. How long something is going to be used or how long it's producing that power. So why is this all important? Well, a solar module can produce a specific amount of power based on sunlight levels, and that amount of power varies constantly based upon weather and seasons and day or night cycles. Because that power level varies, the only way to know how much electricity is produced during a year is to calculate the sunlight power over time. That's energy. Energy values can be summed over a time period to get the total energy used or produced. This helps us compare the energy demand to the energy production. So how do we put this all together? Well, let's look at a few examples. First, let's look at a photovoltaic module that produces 38 volts and 5.68 amps under full sunlight conditions. If we multiply the voltage of 38 volts times the current produced, 5.68 amps, we get 215.8 watts. If it does this for an average of 4 hours per day, we multiply the 215.8 watts by the 4 hours, and it would produce 863 watt hours per day. And if it does that for 365 days per year, we multiply the 863 watt hours times the 365 days per year, and it produces 315,126 watt hours, or 315 kilowatt hours. Our next challenge is to figure out precisely how much energy is actually hitting the Earth's surface so we can collect and convert that solar energy into solar electricity. That's going to be in future lessons on figuring out this actual sunlight level or insolation value. So now you should be able to define power and energy, so you can then calculate that power and energy using voltage, current, and time measurements, and interpret the difference between instantaneous time measurements for power and time of use measurements for energy.